Welcome back to Wood Engineering. I'm Jeff Orochko from Carleton University, and in this video, we're going to continue our beam design example for a Glulam beam by continuing to figure out all of the shear and bearing resistances for the beam. So up to now, we had this simply supported beam. You want to check the first video so that when we talk about the all the input parameters and finding out the loads and then checking deflection criteria and picking a trial beam, and then confirming the bending resistance of the beam, which is what we've done so far. So now what we're going to do is continue and look at what is the shear resistance of this beam. And we are talking about the longitudinal shear resistance because we don't have any notches. Of course, if we had notches, we would still check the longitudinal shear resistance, but we would also have to check the fracture shear resistance of the section at the notch. Okay, so how are we going to calculate our shear resistance? We have a number of options, which we talked about in the shear resistance videos. First, what we're going to do is check our beam volume, because that will determine which options are available to us. You know, our beam volume is just D times B times L, 646 times 130 times our L, which is 7,500 millimeters. Now this is going to give me something in millimeters cubed, and I'm going to convert that to meters cubed directly by dividing by 1,000 three times, and I get 0.6 meters cubed. So this is smaller than 2.0 meters cubed. Therefore, we can use the simplified method to calculate shear. And that is what is being used in the selection table that we just looked at. Since the volume is less than 2, Z is the volume, less than 2.0 meters cubed, can use the simplified shear resistance equation. Okay, so whenever I can do this, it seems to me that it would be wise to do this, because if I do this check and it satisfies, then that's all that I have to do. I'm done my shear resistance, and this is a very easy equation to calculate. Now, in our case, if you recall, we had a factored shear of 101.6, and our shear resistance was, for 130 by 646, ever so close to that 101.0 here. And so we may undershoot our strength a little bit. But we have some things in our back pocket that we can use to squeeze a little bit more shear resistance out of our calculation and prove that it's actually safe. So let's start with the simplified shear. And you'll recall that this equation is just VR phi FV 2/3 AG for Glulam. We used AN for lumber. And this gives us 0.9. FV was, I think, 2.0 MPa. And we had 2/3. And our AG is just B times D, which is 646 times 130. And what do we get when we do this calculation? We get 100.8 kilonewtons. Okay. By the way, this here, I didn't do this calculation explicitly, but this is capital FV, which is small fv times 1 times 1 times 1 times 1. Since we had no service condition factors and no duration factor is 1.0, and no treatment and no system effect. Okay, so this is unfortunately a little bit less than our VF, which happened to be 101.6 kilonewtons. So this is a full kilonewton lower than the limit. It's pretty close, but good news is we can, especially since it's close, we have easy ways to fix this problem. So here is the note. Okay, so we have three options here. The worst option is go ahead and pick a bigger beam. Now, if I was way off on my shear resistance, then this would probably be the best choice, but I'm really close. So I can use either of the other two. The first one, which is number 2 in those options, is I can remember that for longitudinal shear, I don't have to check the V at the support, because most of the load that is at the support is going straight to the reaction through compression perpendicular to grain. So the standard allows us to actually check VF at a distance d away from the support, which is the depth of the beam, equal to the depth of the beam. In this case, that's 646 millimeters, so that will reduce our shear a little bit, probably, depending on our loading condition, obviously. In some cases, that won't change anything. Like if I had a point load in the center of the beam and just 2 reactions, then the shear is constant from the center of the beam to the reaction, so VF at D is not going to have any reduction. But in this case, since I have a distributed load, my V changes, so it's highest at the reaction, and then it goes steadily down with the W, changing the V as it goes. So that is something that will probably make a difference for us. My other option is, instead of using VR, I can use WR. Now, I made the point in the shear resistance video that WR can actually be over-conservative for beams that are less than 2.0 meters, but that kicks in really for very small beams. So in this case, probably we can squeeze something out with WR by using the more detailed calculation. So we're going to do both of these, number 2 and number 3. They will both actually solve our problem. So we only need to really do one or the other, but I'm going to show both just in the interest of showing you how it works. So let's start with option number 2. So previously we called that VF star. Let's draw our shear force diagram. Okay, so this I am not going to discuss exactly how we do this. You will be familiar with this shear force diagram from your structural analysis course. This is VF in kilonewtons. And in this case, remember that our VF here was 101.6, and it is the same over here, 101.6. So this is what our shear force diagram looks like. So now, instead of using the shear at this point here, we're going to go D away and find the shear force at that location. So D here is 646. Our total length, as we recall, is 7,500. So you see it's like a very small distance away relative to the total length, but let's just see what we get. Okay, so I'm going to use similar triangles to do this. Okay, so what is this length here? This is, right, 7,500 divided by 2, 3750, is it? Yep, 3750 millimeters. So this distance here is 3750 minus 646, and I get 3104 millimeters. This is 646. This is the location here that I want to find my shear. I called that before VF star, the factored load at D from the support, and I'm going to use similar triangles for that. So I'm going to say that VF star divided by 101.6 is the same ratio as 3104 divided by 3750. And if I do that, I get a VF star of 84.1. Brilliant. Okay, so now our VR is going to be equal to, remember what we calculated, we can use this VR from simplified shear of 100.8. So if our VR is 100.8, kilonewtons is greater than our VF at D away from the support, which equals 84.1 kilonewtons. So therefore, problem solved. Problem solved, and the beam's okay as is. Excellent. So that's our first option for squeezing some strength out of the beam. Now, do I always have to consider VF at D? No, I mean, if I have my VR, if my highest VF is at the support and my VR satisfies that, then do I have to check VF at D? No, not necessarily. Unless your VF at D is higher than the VF at the support, in which case that would have been what you were using from the beginning to check your VR, because we have to check our highest VF no matter what, unless it's within D of the support. So we are good to go. Okay, so I don't have to always do this calculation every time. If I satisfy the even worse case, which is VF at the support, you know, that's fine. It's conservative, like maybe moment is what is governing my design. Okay, so let's look at the next option. Okay, so that's one way to do it. Here is an alternate approach. By the way, in the clause for shear, this one is called, this one is approach B, and this one is approach A, I believe. Okay, so we can do the detailed shear calculation instead of doing this, and we can probably squeeze some extra strength out that way. So remember that this detailed shear calculation is based on the total factored load, not the shear. So that means that we need to find out what the total factored load is, which is our capital WF, which is WF times L. In this case, you know, depends on your loading condition, obviously, how you calculate your total factored load. In this case, since we have a uniformly distributed load, I'm just going to multiply that by L. You remember that this was 27.1 kilonewtons per meter, and my L is 7.5 meters. So I get here 203.3 kilonewtons. So that's my total factored load. This is all the load that is on my beam. Okay, so now remember what the WR calculation looks like. It is like this. We have my phi, FV. FV is the same, 0.48 times AG times CV, which is our shear load coefficient, times Z, which is our volume to the power of negative 0.18. And our volume has to be in terms of meters cubed. And we already calculated what that was, and it was 0.6 meters cubed. Okay, so our FV, our phi is the same, which is 0.9. Our capital FV is equal to 2.0 MPa times 1 times 1 times 1 times 1. Okay, then our AG we calculated before, which was, I never actually gave what the actual value is. Perhaps I'll do that here, which is 130 times 646, which gives us 83,980. And our Z was 0.6 meters cubed. And our CV is the last thing that we have to do. And we have a couple ways to calculate what our CV is. And for the purposes of showing an example, I'm going to do both ways. Okay, so the first way to do CV is to get it from the tables. Okay, and in our case, we have no point loads, and we only have a uniformly distributed load. So I'm going to go to the shear load coefficient tables. And in this case, it is the first one. So we have shear load coefficient CV for simple span beams, which is what we have, simply supported beam. Okay, number of equal loads, symmetrically spaced. Okay, so we have 0, and that's going to come into play in R, so just hold tight for a second. We need to know what is the total of concentrated loads divided by the total of uniform loads. So we don't have any concentrated loads, and all we have is uniform loads. So the value of R is going to be 0, right? So if I come up here for R of 0, I get 3.69. You see, regardless of how many equal loads I have, because R equals 0 means I don't have any equally spaced point loads. So that means that my CV is going to be 3.69 if I use this approach. It's going to be CV equals 3.69. Okay, in 08614, that's table 7.5.7.5 A. Or another way that I could do it is from this table. You see I'll get the same value because this is for distributed loads. If P min equals P max, so I have a uniform load that is constant over the length, then P min divided by P max equals 1, and then I get 3.69. So it's the same value either way. So that's good that it's consistent. Or B. In CSA 08619, their same tables are there, it's just a different number. Pretty easy to find. Okay, so that's one way to do it. Let's also look at doing it the other way when we had to do the calculation. Okay, so alternatively, calculate manually. Okay, so we're going to calculate CV manually. So you'll remember that what we have to do is for each segment, we have to break it up into segments. And then we have to find the VA, the VB, and the VC, which are the beginning, end, and middle of the segment respectively. And then we have to calculate our G for each segment, and then we have to add them up. Okay, so we haven't seen an example of this yet. So if I go back to my shear load diagram, which I had up here, I'm going to divide this up into two different segments. So let me just draw it out again quick. And one thing that we mentioned when we were doing that is that all the values have to be positive. So if I were to draw my shear load diagram, but the absolute value of that shear load diagram, then I would end up with something like this, right? Because usually it came like this. Okay, but I just made it positive because for the purposes of calculating CV, I use the absolute value of the shear. Okay, so I have two different segments. This was 101.6. This was 101.6, as you recall. And I have segment 1 here and segment 2 here. And these two segments are the same. So I'm going to get the same value for G from both of them. So I only have to calculate one. So if I look at segment 1, so I have 101.6 at A. I have 101, so this is VA. I have a 0 for VB. And at the center, I have 50.8 kilonewtons for VC. Okay, so remember I need to find the VA at one side, VB at the other, and VC in the middle. And if VA and VB switch sides, it's not going to make any difference, which we're going to see in G. But it is important that we identify which one is in the middle and that one is VC. Now, I also have to remember that when I do this calculation, I have to input these values in newtons. So this has to be 101,600 newtons, and VB is 0, and VC has to be 5,800 newtons. And if I don't input it in newtons, it won't work. So it says specifically in that method that it has to be in newtons. And the length of the segment, which we also need, is going to be half of 7,500, which is 3750 millimeters. And that's the same for both segment 1 and segment 2. Okay, segment 1 and segment 2 are identical. So now I know my VA, VB, and VC. I can calculate my G, G1. Okay, and remember this is LA, VA to the 5 plus VB to the 5. So you see it doesn't matter if VA and VB are switched because they're exactly the same term in this equation, but VC has a factor of 4. So if I do that calculation, I'm going to get a gigantic number, and that makes this approach pretty awkward. But it's 45.7 times 10 to the 27. Okay, and this is in units of newtons to the 5th times millimeters. Okay. Super awkward. Okay, so now since segment 1 and segment 2 are identical, then G2 is also the same. 45.7 times 10 to the 27 newtons to the 5 times millimeters. Okay, and my length, my total length, so then to calculate CV, my equation looks like this. This is a stationary load. So I have WF here in my equation, which is my total factored applied load. And I multiply that by L divided by sum of all the G's to the 0.2. So if I sub that in, WF in newtons is 203,300. So that's newtons. Let's keep track of our units here. Then the total length is going to be 7,500 millimeters. And down here, I'm going to have basically 2 times 45.7 times 10 to the 27 newtons to the 5th millimeters. And this is all going to be to the negative, no, not negative, just 0.2. Okay, so the millimeters are going to cancel out in this, just if we follow the units, these millimeters are going to cancel out. And the 0.2 is going to cancel out to the 5, right? So it's going to be n to the 5 to the power 0.2 is those two multiplied by each other, those exponents multiplied. So I'm going to get n to the 1, which is then going to cancel out the n from the 203,000 newtons WF. Right, so this is going to cancel out those two. Okay, but I'm not going to actually write it like that, so that's not confusing in the notes. So if I do this, I find a CV of 3.57. Okay, so isn't that funny? It doesn't actually come out exactly to what we would expect up here, the 3.69. I think that's because of the effect of the WF and everything. It doesn't come out exactly the same, but still pretty close. Okay, so now that we have our CV, I'm going to use that one since we worked so hard for it. I mean, it's a bit worse. Obviously, it's going to give us a lower strength. It's a lower CV than what we had in the table, but we worked so hard, dang it. Why don't we use it? So WR then is going to be our phi, which is still 0.9. times our FV, which was 2.0, MPa times 0.48 is a constant factor in the equation, times our AG, which was 83980. Times our CV, which is 3.57. Times our Z, which is 0.6 to the power of negative 0.18. And if we do all of that, we get 281.1 kilonewtons. And we compare that, WR, which is our resistance to total factored load, to our WF, which was 203.3 kilonewtons. So, okay. So to sum up, we did our original simplified method. We found that WR was not greater than WF, so we had a bit of a problem. So then we looked at 2 ways to increase our calculation of the strength. One was to use VF at D, and the other one was to use the detailed calculation method. And both of these methods worked to juice our numbers a little bit and get a higher resistance. And you see, like when I use this detailed method, you can see how far above the resistance I am. Quite a ways. So this is pretty safe beam. Okay, so that's it for shear resistance. So we have satisfied ourselves that the shear resistance is fine. The last thing that we have to check, since we've looked at bending, shear, and deflection so far, is our bearing resistance. And we're going to want to find what is our minimum bearing length. Okay, so what is our bearing load that's being applied? In this case, QF is just equal to VF. Since I don't have a continuous beam or anything, it's just the shear at the end of the beam happens to be the resistant, like the factored bearing load. This is not always the case. Okay, so in this case it is that QF equals VF, and that was 101.6 kilonewtons. And I cannot use VF at D for this. I have to use the actual load at the bearing, because that bearing is seeing that full load. Okay, our FCP, our capital FCP, it was small FCP times KD times KSCP times KT. I don't have a system factor here, so there's no such thing as system factor for bearing. And so this is 7 times 1 times 1 times 1, and I get 7.0 MPa. Okay, so let's remember that we, our equation for QR, this is for effective all applied loads, is phi times FCP times AB, which is our bearing area, times KB times KZCP. And what we're going to want to do here is rearrange this to solve for AB min, our minimum bearing area required, which is going to be QR divided by phi FCP KB KZCP. Okay, so this is for the all applied loads case. And we're going to deal with the loads near a support in just 1 second. Okay, because that one is a little bit tricky. Okay, so we have capital FCP, we need KB. We're going to assume that KB is 1.0 because we're going to assume within 75 millimeters of the end. Okay, so that makes sense because we're considering that our beam is going to bear something here, and that bearing is going to be right at the end of the beam, so we don't have any length of bearing factor. Our KZCP, which is our size effect factor for bearing, we are going to have to figure out what is the aspect ratio of the top ply of our piece of glulam, and we're looking at 130 by 130 by 646. So the top ply is going to be 130 wide, which is wider than this example that I have here. It's like a 2 by 6 almost, right? And it's going to be about this wide, and the thickness, we're going to assume that it's 38. So what is our aspect ratio? It's going to be B, which is my 130 divided by, we're going to assume 38 millimeters. And that's going to give an aspect ratio of 3.4. So if I go to the KZCP table, if I can find it, yeah, here it is. Okay, the KZCP table, if our ratio of member width to member depth, where in this case our member depth is the thickness of the ply, as you recall, is 2 or more, which it is because ours is 3.4, then our KZCP equals 1.15. So, oops. So this is greater than 2.0, therefore KZCP equals 1.15. Good to go. Okay, so we're going to set QR in our equation to QF to find our required bearing area. Okay, so if I sub in all those things, I'm going to keep track of the units explicitly this time, just to give you another example of how it works. So I have 101,600 newtons on the top, which was 101.6 kilonewtons, our applied load. On the bottom, I have 5.9 FCP 7.0 MPa, which remember is newtons per millimeter squared, times 1.0 for KB times 1.15 for KZCP. So newtons divided by newtons per millimeter squared is going to give me millimeters squared. So that is very good. So my AB min is going to come up to 15780 millimeters squared. So then if I assume that my bearing is on the full width of the member, which should be a very good assumption because I have my member here and it is bearing on a certain bearing location. Presumably that bearing surface is at least this wide, and probably it's wider, which means that the bearing area will be the total width of this times whatever is the length of the bearing. So this is going to be constant. So this is 130 in our case. So if I'm trying to calculate my bearing length, LB min, then I'm going to have my AB min divided by my B of my member, which is 15,780 divided by 130. And I get 121.4 millimeters. Well, too many figs again. So 121 millimeters. So that means the length of my bearing has to be at least 121 millimeters, which is 5 inches. So that's pretty big. Okay, so therefore we need a bearing length of at least 122 millimeters. Okay, so now we have this question of loads applied near a support. Because how do we go about calculating a minimum length for loads applied near a support? What we're going to basically do is we're going to assume that we have this length, 122 millimeters. Then we're going to check the loads applied near a support. And as long as this assumed length satisfies the QR prime check, then we're going to be okay. That would mean that basically the length required for QR prime is less than the length required for QR. Okay, so let's do that check. Here's a note. Okay, so we're going to look at loads applied near a support. So this is the squeezing case. We have a bearing here, and we have loads on top spread out over the entire length of the beam. So that distributed load, the portion of the distributed load that is near the support, just here, is going to cause that squeezing load. And so we need to check that the squeezing resistance is adequate, which is the QR prime resistance, which is 2/3 basically of the QR resistance. And since most of the load is not here, more than likely this is going to be no problem. So we're just going to go ahead and check it. And so again, we're going to assume that the load on top here within D of the support is bearing on the full surface, so the full width of this beam. So we're going to assume that the width of that bearing is just B. And on the bottom, we're going to assume that we have the bearing length and width that we just assumed when we calculated what is the minimum bearing length and width that we need on the bottom using the effect of all applied loads checked. And if that satisfies everything, then that's fine, because if we had a larger bearing surface, it would also be fine. It would not reduce the strength of effective loads applied near a support. So as long as the minimum works, then this check is going to be fine. So let's find the total length of the beam within D of the support. Okay, so why is this LB min divided by 2 plus D? That's because I have to find the center of this bottom support. So that support is at LB min is the total length. The center of that is LB min divided by 2. And then, so that means that that's this portion, the portion to the outside of that, and then on the other side we're going to go a distance D. So LB min divided by 2 plus D is the total length of the load on top of the beam. Okay, so this is going to be, what was our LB min was 122 divided by 2 plus D is 646. And what we get is 706. Let's call that 707 actually, millimeters. So that includes, again, includes the area to the left, or to the outside, if we're talking about the left one, to the outside of the support center. So that's the total length of the load. So then what is our QF for the support? Remember, our QF that we compare to QR prime is just that portion of the load that goes directly from the top to the bottom, because the rest is transferred in shear, a check that we already did. So QF of the support is going to be just our WF times that L of the support. And that is going to equal, what was our WF again? Got to go way back for that. It's 27.1 kilonewtons per meter. And the length of that support is 0.707 meters. And so we get 19.2 kilonewtons. So again, this is what our situation looks like. I'm just going to draw it so that we have an idea. Maybe I'll make it a bit deeper. Okay, so we have our load here. It's our total load. This continues. we have our here, this is LB min. And we need to find out which loads we need to include within D of the support. So we're going to go out here for D. And we need to include this entire surface here because we have D on both sides, right? So on this side, D goes this way, goes off the edge of the beam. And so this total length here is our L support. And the W that is within that WF times L support is basically our total load that is for checking our squeezing load. So it's just those red arrows that happen to be within that L support length. Okay, good. So now all we have to do is do the check. Okay, so remember that QR prime is 2/3 times phi times FCP times AB prime, which is our effective bearing area, times KB times KZCP. AB and KZCP are still the same as they were before because nothing has changed. AB prime is going to equal B times LB1 plus LB2 over 2, where B is our average bearing width, and that in this case is the actual bearing width of the beam on both sides. LB1 is basically LB min, which is 122. LB2 is the L support, which is 707 divided by 2, and we get 53825 millimeters squared, but we have to make sure that that is less than or equal to 1.5 times B times LB1, which is LB min, which equals 1.5 times 130 times 122, which equals 23,670 millimeters squared, which is quite a bit less than the AB prime. So therefore, AB prime is capped at 23,670 millimeters squared. Okay, good. So now I can do my QR check. QR prime is 2/3, phi is 0.9, FCP was, then our AB prime is 23,670, our KB was 1.0, and our KZCP was 1.15, and I do that full calculation, and I get QR prime is equal to 101.6 kilonewtons. And I'm going to check that against our QF support, which is the applied load that we're checking that against, only that load that goes directly between the top and bottom of the beam, which was 19.2. So that is way bigger. So, okay. And as we expected, effect of all applied loads governs in this case. And that's because most of our load is not near the support. Most of our load is away from the support in this case. And so effect of all applied loads governs. We calculated what the LB min for that was. And so that means that minimum bearing length for design is 122 millimeters. And that is basically the conclusion of our bearing design. So we just have to make sure that whatever bearing we design has a length of at least 122 millimeters, as long as the full bottom surface width of the member is in that bearing length. Okay, so that's it. So now we've totally done our design. Our final design is and we should state this is a Douglas fir larch 20F-E 130 by 646 beam with bearing length at least 122 millimeters. And I can go at it, I could draw that as well. I think this is pretty clear. There's not that much that is confusing about this. So that's it. So over these two videos, we have looked at how to calculate the applied load and shear, and how to calculate what our minimum ESI is for deflection. Then we selected a beam section from the tables in the design manual. Then we looked at our moment strength to make sure that that satisfied our applied moment. We looked at our shear strength. We looked at how to increase our shear strength a little bit by using alternate methods to look at either VF at D or using the detailed method for shear. And then we looked at calculating what our minimum bearing length is. And after all of that, we've come out with a beam design that is adequate for what we were looking for.